We begin with certain problems. Find the locus of a point P which moves so that its distance from a fixed point C1, 2 always is a constant, which is 5 units. The process of writing or representing this locus in coordinate geometry is that we try to express the path followed by it in terms of an equation, which is an algebraic equation in terms of the coordinates x and y, the distances of a moving point from the two mutually perpendicular lines. First, let's see how the locus is. There is a fixed point C, this P is moving so that CP always is remaining a constant. We have already seen that this traces a circle. In coordinate geometry, what we do is we try to represent this geometric figure with the help of an equation. So we let the coordinates of the moving point to be some x, y, that is let px, y be a point on locus. Now we express the geometric condition as an algebraic condition. The condition is that Cp is equal to 5. That is root of x minus 1 square plus y minus 2 square is equal to 5. Squaring on both sides, we see that this becomes x minus 1 square plus y minus 2 square is equal to 5. When I expand, I have x square plus y square. The cross product term here is minus 2x. The cross product term here is minus 4y. The constant term here is 1 square plus 2 square is 5, and 25 comes here. The constant becomes minus 20 is equal to 0. So this becomes the equation of the locus px, y. That is, when we plot this on a graph sheet, we see that we get a nice circle of this form. Problem number 2. Let A and B be two given fixed points. The locus of point P which moves so that PA is equal to PB. We have seen that this is going to be a straight line which is the perpendicular bisector of AB. So as usual, to represent the locus in the form of an algebraic equation, we start with assigning general coordinates x, y to the moving point. That is, let px, y be any point on the locus. The geometric condition we have is PA is equal to PB, or root of x minus 1 square plus y minus 2 square is equal to root of x minus 5 square plus y minus 6 square. Squaring on both sides and rearranging the terms, we can get it to the form x minus 5 whole square minus x minus 1 square plus y minus 6 whole square minus y minus 2 whole square is equal to 0. So you can employ now the formula a square minus b square is equal to a plus b into a minus b, which simplifies this. A plus b gives you 2x minus 6. A minus b gives you minus 4. A plus b here gives 2y minus 8. A minus b here gives minus 4 is equal to 0. So this minus 4 gets cancelled. 2 gets out as a common factor from throughout. We have nice simplified equation in the form x plus y minus 7 is equal to 0. So on a graph sheet, if you locate the points A and B, and when you plot this line equation, we see that that is going to trace the perpendicular bisector. See, something like this. Assume that this is the graph sheet you have. A is 1, 2, a fixed point. B is 5, 6. Then the trace of this perpendicular bisector this will be the locus of P. X plus y minus 7 is equal to 0, which is going to be the perpendicular bisector of AB. Problem number 3. Given two fixed points A and B, find the locus of P so that PA plus PB is 12. So as usual, we assign the general coordinates x, y to the moving point. That is, let Px, y be a point on locus. The given geometric condition is that PA plus PB is a constant, which is 12. When we write this as an algebraic equation, this becomes root of x minus 0 square plus y plus 4 whole square plus root of x minus 0 square plus y minus 4 whole square is equal to 12. Now you could recollect a trick which often it is used in manipulating the quadratics. That is, whenever you have root a plus root b is equal to k to solve an equation of this form where a and b both these are quadratics. Particularly when coefficient of x square y square in this and in this are same. What we do is we write root a minus root b. This expression can easily be obtained by multiplying both these sides by root a minus root b, and we can get root a minus root b. Once root a minus root b is obtained, we can take this as one equation. This is second equation. By simple addition, we get 2 root a becomes equal to something, and squaring we have a relation connecting x and y. So we shall employ this trick here. We see that coefficient of x square in both these a and root b are same, also the y square. So we multiply both sides now by root a minus root b. Then we have an expression which is of the form 12 into, I am multiplying both these two sides by root a minus root b. Root of x minus 0 square plus y plus 4 square minus root of x minus 0 square plus y minus 4 square is equal to. Now when root a plus root b is multiplied with root a minus root b, what we have is simply a minus b. So a minus b terms here will get simplified to x square will get cancelled. The cross product term here and here, which give you 8y and 8y, makes it 16y. I bring this 12 to this other side. When I add, I get 2 root x square plus y plus 4 square is equal to 12 plus 16y by 12. So we can cut off this 2. This becomes 6. This becomes 8. When I square now, I have x square plus y plus 4 whole square into is equal to 6 plus, there is further simplification here. 4 goes 2 and 3 times, 2y by 3 whole square. So this becomes 9 into x square plus y plus 4 whole square is equal to 18 plus 2y whole square. We can simplify this further as 9x square plus, when 9 goes inside, 3y plus 12 whole square minus, I bring this to the other side, 18 plus 2y whole square is equal to 0. I can apply here the formula a square minus b square, which is a plus b into a minus b. Therefore, the simplification would be 9x square plus a plus b gives me 5y plus 30. A minus b gives me y minus 6 is equal to 0. Therefore, this gets nice simplified form, which is 9x square plus 5y square. The cross product terms will get cancelled, is equal to 180, or x square by 20 plus y square by 36 is equal to 1, which is an ellipse. So the equation that we got is, the simplified form of it is x square by 20 plus y square by 36 is equal to 1, which is going to be an ellipse. We shall see the trace of this. Let this be 0, minus 4 and this be 0, 4. These two are fixed points. P is the moving point x, y. When P moves satisfying this particular condition, the trace of it, you can observe that this is an ellipse. So we have just now seen that whenever P moves, so that PA plus PB is a constant, the locus in general is going to be an ellipse. However, in an exceptional case, when this constant k is AB, where A and B are fixed point, P is the moving point, then this locus turns out to be the segment AB. We shall try to realize this. We make use of the triangular inequality. Let's try to recollect. If ABC is a triangle, then sum of any two sides necessarily has to be greater than the third. That is, AB plus BC should necessarily be greater than or equal to AC. This equality occurs whenever this A is collinear with BC. So here in this example, we are given A as minus 2 comma 0, B as 2 comma 0. Therefore, AB is 4 and that is PA plus PB. Therefore, here we conclude that the locus is the segment joining points A minus 2 comma 0 and B 2 comma 0. That is the locus. Problem number 5. Here we are given 2 points A and B. We need to find the locus of a point P which moves so that PA minus PB is a constant. Now in general, whenever A and B are two fixed points, the locus of a point P which moves so that PA minus PB is a constant in general traces a hyperbola. And in an exceptional case, when this K is AB, we see that the locus is set of points on AB, extended line AB, excluding the segment AB. Now here, when we find AB, we see that, let's take B to be 3 comma 0. When we find AB, we see that this AB is not 3. Therefore, we are referring to the case of hyperbola. So let's try to simplify this. So we have the fixed points A as minus 3 comma 0, B as 3 comma 0, and we need to find the locus of P which moves so that PA minus PB, this K here is 3. So when we let the general coordinates x comma y to P, that is let Px comma y be any point on the locus. When we write the condition in the form of an algebraic equation, PA is root of x plus 3 whole square plus y minus 0 whole square minus PB is root of x minus 3 whole square plus y square is equal to plus or minus 3. Because mod x is equal to 3 implies x is equal to plus or minus 3. So here we solve the two cases when it is equal to plus 3 also minus 3, and then we see that by symmetry it follows that in both the cases we end up with the same equation. So let's go ahead with plus 3. This equation, when you look at it, it is root of a quadratic minus root of another quadratic is a constant. To solve equations of this kind, we try to multiply both sides by root of A plus root of B so that we can get the value of root of A plus root of B is equal to another constant or an expression in x, because we see here that the coefficients of x square and y square are exactly similar. Therefore, when we multiply these both, we see that, or when we find the value of root A plus root B, we see that it will be independent of the quadratic terms. So that is the trick that we use. It is a popular trick in quadratic manipulations. So from this, when we multiply both sides of this equation with the root of A plus root of B, this turns out to be 3 into, I write the right side first here, 3 into x plus 3 whole square plus y square minus x minus 3 whole square plus y square. This is what I get when I multiply both sides with root A plus root B. 3 times of it will become x plus 3 whole square minus x minus 3 whole square it is something like a plus b whole square minus a minus b whole square, which is equal to 4ab. Therefore, here it becomes 12x. Y square terms will get cancelled. So I can remove this 3 and make it 4. Now when I add these both relations, I get 2 times root of x plus 3 whole square plus y square is equal to 4x plus or minus 3. Now when I square on both sides, I get 4 into x plus 3 whole square plus y square is equal to 4x plus minus 3 whole square. Further simplification yields me this 4 can be pushed inside. So I can then write this as 2x plus 6 whole square minus, I can bring this to this side, which is 4x plus or minus 3 whole square plus y square is equal to 0. So this is something like a square minus b square, which gets simplified to a plus b into a minus b. A plus b, when I write, it is 2x plus 6 plus 4x plus r minus 3 into the difference of it. When I write, it is 2x plus 6 minus 4x minus r plus 3 plus y square is equal to 0. So this becomes 4x plus 2x is 6x. 6 plus or minus 3. If I take plus first, then I have to take minus here. So when I simplify this, 6x plus 9 into minus 2x plus 3 plus y square is equal to 0, which simplifies to minus 12x square. The cross product terms we see here that they get cancelled because 18x will get cancelled. So what we have is only the constant term, which is 9 into 327 plus y square. However, if I take minus here, that is here minus means it becomes plus here, right? So when I simplify this possibility, 2x plus 4x is 6x. 6 minus 3 is 3 into 2x minus 4x is minus 2x. 6 plus 3 is 9 is equal to 0. Now when I simplify this, I have 12x square. Here again we see that the cross product terms will get cancelled. Plus y 27 plus y square is equal to 0. I can see here that these both are giving me the same equation. So this becomes the equation of locus of px comma y, which satisfies the condition that pa minus pb is 3, where a and b are given by a is minus 3 comma 0 and b is 3 comma 0. Problem number 6. Here we see that we are given the same condition, pa minus pb is a constant. However, we see that this constant is 8, which is the distance between a and b. That is, this is ab. Now whenever pa minus pb is equal to ab, the locus turns out to be the set of points on the extended line AB excluding segment AB. We shall try to realize this. Consider a triangle AB and P. Now triangular inequality says the difference of any two sides always is less than or equal to the third. That is, PA minus PB always is less than or equal to AB. This equality occurs when P is collinear with AB. This equality occurs whenever this P is collinear with AB, so that we can see AP minus PB will be exactly AB. The maximum of this is itself AB, then P should lie on the line segment AB, excluding the points which are between A and B. So the answer to this question is the locus of P is set of points on the line AB extended excluding the segment AB. That is, if A is here, which is minus 4 comma 0, B is here, which is 4 comma 0. When I draw this AB, locus of P is set of all these points which are belonging to the extended line AB excluding this particular segment. So this happens whenever PA minus PB is exactly AB. If it is not, we have seen in the earlier example that in general it turns out to be a hyperbola. Problem number 7. This is an instance which gives us the locus as a parabola. Let S be a fixed point. We need to find the equation of locus of a point P which moves so that its distance from x-axis is equal to the distance of it to the fixed point S. So as usual, we assign general coordinates px comma y to the moving point P. That is, let px comma y be a point on locus. The geometric condition now, when we write it in the form of an algebraic equation, the distance of this point P to the S, which is SP, that should be equal to the distance of the point P to the x-axis. Now distance of the point px comma y to x-axis is mod y. This is already known. So this is the condition we have. SP is root of x minus 1 square plus y minus 2 square is equal to mod y. Squaring on both sides, we have x minus 1 square plus y minus 2 square is equal to y square, or x minus 1 square plus y minus 2 square. I bring this y square to the other side is equal to 0. Here again we have an opportunity to use a square minus b square, which will be equal to a plus b into a minus b. That is x minus 1 whole square plus sum of them is 2y minus 2. The difference of them is minus 2 is equal to 0, or this becomes x minus 1 whole square is equal to 4 into y minus 1. This is the equation of locus of px comma y. We shall have a trace of this. Let's say these are the coordinate axes ox, oy, and we have a point S, which is, we need to trace this curve. So basic equation is something like ax square is equal to 4y, where x and y are displaced by 1 unit. So I locate the point 1 comma 1, and this is an upward parabola. Problem number 8. Find the locus of a point which is at a distance of 3 units from y-axis. So let's first geometrically visualize how the locus is going to appear. Let's say these are the basic coordinate axes ox, oy. We need to now collect all the points which are at a distance of 3 units from y-axis. Obviously, if I move 3 units, I approach to the point 3 comma 0. So this is a point on the locus. Also to the left, I can get one more point which is there on the locus. Now distance between two parallel lines always remains the same. Therefore, all the points which are there on the vertical line, which is x is equal to 3, are going to satisfy this particular condition. Also, the points which are there on the vertical line x is equal to minus 3 are going to satisfy this particular requirement. So P can be any point here or any point here on this. We shall now try to get an equation of the locus of a general point Px comma y which satisfies this particular condition. So as usual, we assign general coordinates x comma y to moving point. So when we write the condition that is imposed on the moment of P is that P moves so that it's a distance from y-axis. The distance of px comma y from y-axis is mod x. This is very well known. This is equal to 3 units. So whenever mod x is equal to 3, x becomes equal to plus or minus 3. This becomes the equation of the locus. And that's what we could get it here. Problem number 9. There are two fixed points given, O, origin, and A with coordinates 1, 2. P is a point which is moving with the restriction that area of the triangle OAP always is 5 square units. So we first derive here the equation, then look at the trace of it. We do the other way here. So let Px comma y be a point on the locus. When we write the geometric condition that area of the triangle OAP is 5. Now area of the triangle OAP is half. So well-known formula 2x minus y is equal to 5, or modulus of 2x minus y is equal to 10, or 2x minus y is equal to plus or minus 10. We can have a combined equation here, that is 2x minus y is equal to 10, or set of all points which satisfy the relation 2x minus y is equal to minus 10. So this or this can be put into one condition saying that 2x minus y minus 10 into 2x minus y plus 10 is equal to 0. So this becomes the equation of the locus. When you trace this on a graph sheet, you see that the locus is pair of parallel lines. I just leave this to the students. Right. Concept number 2. When the coordinates of the moving point P, x comma y are in turn, if they are expressed as a function of a parameter, then the Cartesian equivalent of it is obtained by eliminating the parameter and getting the relation connecting the coordinates of the point Px comma y. That is, if x is equal to f of t and y is equal to g of t are the parametric equations. That is, x and y expressed as functions of a parameter. T here is the parameter. Equation of locus of this moving point x comma y now is obtained by eliminating the parameter. If I call this as equation 1, equation 2 from equations 1 and 2. So when we eliminate t from these, we get a relation which connects x and y, which itself becomes the equation of the locus of the moving point P. Then we call that equation as the Cartesian equivalent of it. Example. Suppose x and y are parametrically expressed as x is equal to 2t plus 1 and y is equal to t minus 1. Now t here is the parameter. To get the Cartesian equation of the locus of this moving point, we eliminate t from these two. This is first relation, this is second relation. The elimination process is very simple. From the second relation, that is from this, we have t is equal to 1 plus y. And when we put this into the first, we have x is equal to 2 into 1 plus 1, or x minus 2y minus 3 is equal to 0 becomes the Cartesian equivalent equation of the locus of the point whose coordinates are parametrically given by these equations. Yet another example, we have x being given as a cos theta, y being given as b sin theta. Now the parameter is, so from these relations 1 and 2, we eliminate theta to obtain a relation connecting x and y, which will represent the Cartesian equation of the locus of the point x comma y. From the first relation, we have cos theta is equal to x by a. From the second relation, we have sin theta is equal to y by b. The elimination is very simple because always sin square theta plus cos square theta is 1, and hence we have x by a square plus y by b square is equal to 1 is eliminated. This itself is the Cartesian equivalent of the locus of this point. One more example, x is equal to ct, y is equal to c by t. So here t is the parameter. This is the first equation, second equation. The eliminant here is very obvious. When we just multiply these two relations, that is when we write x into y, we see that t is at once eliminated. So we have xy is equal to c square is the equation of the locus.